Hello everyone, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is your MCQ and the question is in front of you. I request everyone please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. I believe we have tried, so let's start. Now if you look at the reagent carefully, this is actually Resorcinol or 1,3-dihydroxyphenol. So actually you can say this benzene ring is electron rich due to the plus R effect of 2 OH group. And if you look at sodium bicarbonate, it can act as a base or it can act as a source of CO2. So let's learn everything step by step. Now, if you look at here, the sodium bicarbonate could be hydrolyzed. What is the meaning of the word hydrolysis? Hydro means water and lysins means breaking. So hydrolysis means you can say breaking by water. So what happened? I can consider water as HOH. This OH is delta minus, hydrogen is delta plus, and here sodium is plus and this bicarbonate is minus. So sodium takes this OH and forms sodium hydroxide, and remaining bicarbonate plus H plus both combine and produce carbonic acid. By the way, carbonic acid, if I say this is actually weak acid, means it dissociates partially into the H plus and HCO3 minus. This dissociation is actually very less. That's why majority of cases the dissociation of carbonic acid is ignored. But if you look at NaOH, it is stood in strong base, or it is called as alkali. Means in water it get dissociated into Na plus aqua and OH minus aqua. And that's why, since H2CO3 is weaker acid but sodium hydroxide is strong base, so in reaction medium OH minus ion concentration is more. Consequently, the reaction medium is basic in nature. And by the way, carbonic acid decomposes easily and it can produce water and CO2. So you can consider sodium bicarbonate solution is actually alkaline source of carbon dioxide. Alkaline medium carbon dioxide source. So now this much you understand, medium is alkaline. And if you look at phenol, phenol is actually weakly acidic. Now acidity of any compound is defined by the stability of its conjugate base. What is mean by conjugate base? If you remove the H plus, whatever the anionic part is remaining, that is called conjugate base or Cb. Now higher the stability of conjugate base, higher is the acidity. Actually this phenoxide has a significant stability because of the plus R effect. So in this way the electron density goes and delocalized inside this benzene nucleus, which provides to some extent stability of the negative charge, means this extra electron density by delocalization. Other canonical forms possible. I request you people try by yourself. So that's why phenol is weakly acidic, and in presence of sodium hydroxide, means this alkaline medium, this dissociation is preferred. Why? Because the H plus is consumed by the produced OH minus and produces water. So in presence of any OH, this dissociation is efficient. Now next point. Now if you look at this actual our compound, that is in case of resorcinol, there is this resorcinol, it's 1,3-dihydroxybenzene. Now one very important point, who is more acidic between phenol versus resorcinol? Actually phenol is more acidic because the second OH is actually an electron donating group. So electron donating group help to destabilize or less stabilize the O minus. So you can see if you remove any one of, by the way both are same, so any one of proton you remove doesn't matter. So it is O minus Na plus. This O minus stability is to some extent less because of the plus R effect of these OH. I mean if you compare with simple phenol. So obviously you can say, sir, it is not a complete deprotonation. You can put a reversible sign here. So partial dissociation or partial proton abstraction to get this phenoxide type derivative. You can think like that. Now, as I told that this sodium bicarbonate could be hydrolyzed and produce carbon dioxide. And this carbon dioxide could be utilized to react with this. I shall come after some time. Now, not only that, directly also this reaction possible, because in reaction medium NaOH produce CO2, so that both. So it is, I have shown this direction stepwise, this direction one step, result is similar. So here very important thing, these moiety, if I say this is comparatively higher electron rich due to the plus R effect of this OH group. So I can say, even if you compare this resorcinol versus this is deprotonated version. This is even further electron rich because one negative charge is on oxygen, and remember negative charge means excess of electron. So if this oxygen has more electron, so it will delocalize more amount of electron density inside this benzene ring. So you can say, sir, benzene ring is more electron rich right now after deprotonation. So that's why you can say it is more reactive towards aromatic electrophilic substitution, since it is more electron rich. So since it is more electron rich or more reactive, then milder electrophile can also participate in aromatic electrophilic substitution. And here CO2 is actually milder electrophilic reagent. So that's why it can participate in a chemical reaction. So what happened? First step, you can expect that okay, this O minus will be produced and later on it can react with carbon dioxide and ultimately aromatic electrophilic substitution can take place. Now, by the way, student, I'm not going to mechanism. If you have any doubt or if you want to learn further, I shall provide link of my previously uploaded video on aromatic electrophilic substitution, basic concept and mechanism. You may visit for further learning. Now a question that regioselectivity, that sir, where the aromatic electrophilic substitution can take place. By the way, student, there are 4 options. Actually, proton will be substituted. So option number 1, 2, 3, 4. Now, whenever you are talking AES, means aromatic electrophilic substitution, electrophile will react at that place which is maximum electron rich. Now the question is position number 1, 2, 3, 4, which one is maximum electron rich? For that purpose, you need to understand one thing, that OH group is ortho and para donating and obviously activating. Now if I say this OH number A, so it will increase the electron density at, obviously it's ortho, this 2 position, and para, this position. Now if you say, sir, what about the other OH? So for other OH, that will increase electron density of these ortho, 2 ortho and para position. Now there is a question that okay, sir, both sides are activated by same. So now how can I decide? When electronic factor is not capable to explain, let's go to the steric factor or bulk factor. Now if you look at with respect to position 1, both sides there is OH. So steric inhibition of resonance can possible, or sometime it is called as ortho effect. I shall provide you some link regarding this concept. So question that because of ortho effect, this one position is sterically not that much accessible. Done. But what about 3C? Option 3 is previously nullified because of the Plasar effect. Now option 4 versus 2, which one will have the aromatic electrophilic substitution? If you look at closely, student, both 4 and 2 are same. So you don't need to think more. Wherever you put the electrophile, ultimately product is same. So let's put the electrophile here. See, if I say this is benzene ring, so it can participate in reaction. Actually, obviously O minus, with respect to O minus, the para position. So you can put O minus anywhere. So let's consider that O minus is provided here. Okay. Now O minus is here, means para with respect to O minus, so here COH. How? So these can push, electron density will come here and it can react with carbon dioxide because this carbon is attached to 2 oxygen atoms and oxygen is comparatively more electronegative than carbon. So this is delta minus, this is delta plus, so aromatic electrophilic substitution take place and this electrophile attacks here and this bond opens. So it produces, actually initially it produces COO minus, and obviously as a counter cation metallic sodium will be there, means sodium ion. Now upon workup it will produce this carboxylic acid. By the way, remember generally H3O plus means either dilute HCl or dilute H2SO4. Generally they are used. Now this is the product upon acidic workup. This reaction is actually an extension of Kolbe reaction. Now you may think, sir, Kolbe reaction I have studied higher temperature, high pressure needed because CO2 is not at all a good electrophile. I agree. In Kolbe reaction we have taken with sodium hydroxide and phenol, means sodium phenoxide. But in this example there is a extra OH there. So because of the extra OH, the ring is comparatively more electron rich. So it is more reactive for ES. That's why comparatively milder condition is enough to react with this milder electrophile, and aromatic electrophilic substitution takes place, this ortho or para position. So this is the logic, that milder condition is enough here for carboxylation reaction. Now what is the major product of this reaction? Obviously this ring with carboxylic acid, B. Now if you think, sir, if I do not know this concept completely, how can I get this reaction? By the way, there is a high mistake of one option. Someone may think, sir, sodium bicarbonate, it is alkaline medium. So what will happen? First deprotonation, again during H3O plus treatment, protonation. So overall no reaction. Student, very careful. Generally we ignore no reaction option, but in this case, if you do not know it properly, there is a chance that you may end up mistake. You have to remember one concept, that this bicarbonate could be weak, means it could be an alkali as well as it could be a source of CO2. So aromatic electrophilic substitution possible under boiling condition. If I say aqueous solution boiling in slightly higher than 100 degrees centigrade, but no pressure. But here that will also result in reaction because there is one extra OH. So because of this reaction, okay, CO2 will react with this benzene ring. If you look at only one option there where CO2 is attached to benzene ring, so this is the answer. Okay, now if you think different angle, so this is a bicarbonate, it can even produce HO minus. If I say HO minus, this is nucleophile, electron rich. So how HO minus can attach to this benzene ring? It's an illogical option. Obviously this benzene ring is even electron rich, so aromatic nucleophilic substitution or nucleophilic attack on this ring is not possible, so it's a wrong option. Now if you look at here, it's aldehyde. By the way, if you look at carbon dioxide, so if you look at carbon here, +4 oxidation state, carbon dioxide equivalent. Now how can it be reduced to this? Okay, for that purpose you need to have a reducing agent. But did I provide any reducing agent? This is just acidic workup, not a reduction. So this is also a wrong choice. So what is remaining? This. That's why I told at the beginning, it is a easy but a confusing. So I guess you have learned a lot. So this is the overall discussion. Thanks for watching. See you in my next video. Bye bye.